Okay. Let us talk about electric fields. Now if I have two charges, if I have, say this is a fixed charge and I put an electron or something there, those two will repel and this will experience a force pushing it away. Now what we call that is that we say is this is in the electric field of that. So what is a field? In physics, a field is a region of space where a force is experienced. So the classic one we're all used to is a gravitational field. So if we're in a gravitational field, gravity, if I have a rock or whatever, a pen, I'll let that go down, that will experience gravity and it will accelerate that way, force due to gravity. So because there's gravity pulling that rock down, we call it, say it's in a gravitational field. Same here, if I have an electron and it's an electric field, then that will move away. So we can say that there's an electric field there. Now how big is this electric field going to be? Well, we know from earlier that the force is equal to K, Q1, Q2, I keep doing that, Q2 over R squared. But if we say, use the test charge of a known size, let Q2 equal 1 coulomb. So the force is going to equal K Q1 times 1 coulomb R squared. So the force is basically 1, if you multiply anything by 1 it cancels, so basically the electric field is going to be equal to K Q1 over R squared, which sounds good. So basically if I stick a 1 coulomb charge in there, it's going to be the same as K Q1 over R squared. And if we actually work through the math at some point, we can say the electric field, and E is the electric field, is going to equal the force over the charge, over Q. So it's going to be force, and force is going to be newtons, this is going to be a charge, so the charge is coulombs, so the electric field is going to be newtons per coulomb. Also later on we'll show you that the electric field is also equal to volts per metre, but at the moment let's deal with electric field is newtons per coulomb. So let's try this. Let's do example, what's that, 4.4 or exercise 4.4. Remember, if you want to try these yourself, feel free to pause these. What is the electric field at a distance of 0.1 meters from a charge of 1 microcoulomb. So, draw a picture. We've got what is the distance from a microcoulomb? Because it doesn't give a sign, that's going to be positive. So it's going to be 1 times 10 to the 6, negative 6 microcoulombs. And it's going to send out lines. And if we stick a charge in here, which we're saying is 1 coulomb, or what's the size of the field going to be? E is equal to K Q1 over R squared, which is equal to, we worked out 8.988 times 10 to the 9 Newton meters squared per coulomb squared times we said it was 1 microcoulomb, 1 times 10 to the negative 6 coulombs, all over the distance of 0.1 meters squared. We stick that into our calculator. 8.988 x per 9 times 1 x negative 6 divided by 0.1 squared equals, what's that? 898.8 kilonewtons. Yep, per kilo. Well, actually, look, let's actually work through this. What's the unit going to be? It's not kilonewtons because it's electric field. So it's going to be, there's our newtons. We've got meters squared below. We've got meters squared below. That coulomb there cancels out one of those. So it's going to be kilonewtons per coulomb. So if I put 1 coulomb in there, it's going to experience 899,000 newtons of force. Cool. Let's try that again. Okay, let's do part 2 of this. If Q is equal to 10 microcoulombs, we can do the same thing. E is equal to K Q over R squared, which is equal to 8.988 times 10 to the 9 newtons per meter squared, newtons per coulomb squared, times 1, or 10 times 10 to the negative 6 coulombs, all over 0.1 meters squared. So again, stick that through our calculator. 8.988 x 9 times 10 x minus 6 divided by 0.1 squared equals 8,988 kilonewtons per coulomb. So basically, if we make the charge bigger, what this is, if I make the charge 10 times bigger, then the field is 10 times bigger. So the field strength is directly related to the size of the charge. But let's just do a little bit on drawing electric fields, because one of the things we're doing when we do electric fields is we like to visualize things. Humans are very visual, so we will draw the lines between fields. So if I have, drawing, there's a few rules of drawing electric fields. So if I'm going to have a positive charge here, we draw them as rays or lines. So basically there's a few rules. A line starts at a positive and ends at a negative. So if I have 2 positive, negative, starts from positive, goes to the negative. Isn't that cool? Okay, so the more lines, the stronger the field. Okay, the lines do not cross. So if I have, for example, 2 positive charges, I'll use red to avoid confusion, these lines will approach, but they will not actually cross. And they don't technically touch either, so it's just my draftsmanship is a bit awful. And if you were to put a test charge, the thing about these lines is if I was to drop a test charge on here, the test charge would actually follow these lines. So if I was to put a proton here, the proton would follow that line as it went away. If I put a proton here, it would follow that line as it went away. If I put a proton, proton here, it would go from there, around there, until it hits there. So lines never cross. The more lines you have, the stronger the field is, the closer the lines are together. So that's and remember must start, so if we have two plates, plus, 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 like on a capacitor for example, the lines would start at a plus, end at a minus. Start at a plus, end at a minus. Okay, so there's just one last question when we're dealing with electric fields. And then we'll have to let you do your own problems and read the textbook. Okay, so what happens if you want to add up? Say I have two charges here. And so I dropped, let's say this is 10 microcoulombs and this is 20 microcoulombs. Let's say they're on a meter apart, 0.1 meters apart. What happens if I put my test charge here? You'll notice that what happens is this will be, if this is positive, these two will repel. And I'm going to make these exactly the same distance, so let's make this one, let's make that 1.1 meter. Let's make that distance 0.1 meter as well. Okay, what we can see is these are going to repel. And because this one is they're the same distance, this one's twice as big, this one's going to repel, be twice as big. So how can you work out the total force or the total size of that field? And that's simple. So if we go E1, E2, force 1, force 2. Remember, force is going to equal, and remember this is a vector, it's going to equal sum of the forces, which is equal to F1 plus F2. Or if we're going to get boring, remember with vectors you add them nose to tail if you're doing it graphically. F1, F2. So the resultant is going to be, so the actual vector for this is going to be, if we use the old classic polygon of forces, or the parallelogram of forces that they love in engineering, we can see that the actual final vector is going to be up here. So basically, because we're creating forces, the electric field is creating forces. Forces are vectors. If you have more than two fields, if you're trying to figure out the influence of more than one of those things, you just add them together using vector addition. So now hopefully that sums up electric fields, and then we'll start getting on to next lecture. We'll do electric potential and such like. So till then.